Hi students, in this video I am going to explain about diode applications and diode switching times. I am Dr. B. Ravi Kumar, Associate Professor, Department of ACE. So far we discussed some of the operation of the p-n junction diode and behavior of this p-n junction diode in forward and the reverse characteristics. So among those operations we can conclude that diode how useful in electronic applications. We will see now what are the applications of p-n junction diode. These are the common applications of the p-n junction diodes. When we see in all the applications, these are the important applications which are going to use in electronic circuits. First we will see that diode is used as a switch or switches. When I am talking about the switches, the exact operation of the p-n junction diode, if the diode is an ideal in forward bias, it perfectly allows the current flow and it will be act as a short circuit, whereas in reverse bias it does not allow any current flow and it acts as open circuit. So simply p-n junction diode, it allows in forward direction and it does not allow an open circuit completely in reverse bias. So that when we use this kind of on and off operations of the diode connected in digital circuits, then it will be used as a switch. And next one is rectifier. So this is also one of the best application for diode rectifiers, because of diode allows only in one direction and it suppresses in the opposite direction. So we can use the diode as a rectifier which allows the forward direction in half-wave rectifier, and in the reverse bias which allows two cycles. So simply we can say that diode used as a rectifier which converts alternating current or alternating supply to direct current or direct supply. Next one is clipping circuits. It is a simple electronic circuit which clipping the required portion of a input sinusoidal signal or cosinusoidal signal. And clampers which boosting DC levels of a required voltage. So when we passing through the sinusoidal signal with the DC value, maybe we start from 0 or some specified values. If you want to boosting that DC level to some other value, when we passing through the clamping circuits, then you will achieve this kind of signal. Then current protection circuits, most of the times of the electronic circuits, before going to give any variation of the signal to the circuits, sometimes this large variation in the signals is probably the reverse voltage, so the circuits gets damaged. So in order to protect that circuit, we can use some kind of diodes in input and the application circuit, and in logic circuit also. These diodes used in logic gates. So as I said that it will be used as a switch. So all the logic gates operated with the switches, logic high, logic low, on switch and off switch. So all are operated with the logic 0 and 1. Then when the p-n junction diode shows a logic 1 when it is connected in forward bias, and it shows 0 and when it is in reverse bias connection. So let us see that each one of them one by one, how the circuit is and how those applications will work. So if you see this here, So this is the rectifier circuit, a simple network which having AC input signal, and it is a rectified circuit which consists of a diode and a load resistor. So actually it's not shown that as transformer. Actually this AC signal given to transformer. So it is a simple circuit by giving this AC input signal, sinusoidal signal. This kind of signal is given to a simple rectifier. So forget about this. It is an half wave or full wave or bridge rectifier. If it is given to simple rectifier, which converts this alternating signal to a unidirectional signal or pulsating DC signal. This kind of signal in half wave rectifier and this kind of signal in full wave rectifier, so that which rectifies from a given AC alternating current, alternating signal to direct current or direct signal. So this kind of signals actually, when we further operated with filters and regulators, then we can get this kind of signal, this full wave rectifier, this kind of signal get in the rectified filter output, and then passing through this signal, whatever this signal, this edge signal, can given to the filters, then you will get the perfect DC. So this is the signal for perfect DC. So this kind of signal will achieve by primarily giving to these rectified circuits. That's why one of the application of this diode. So one of the heart of the rectifier is diode. So when we use this diode in rectifiers, then we can we can say that the diode used as a rectifier. So and then coming to the next application, clipper circuits. So if you see this kind of circuits, clipper circuit, just it uses one diode and a bias resistors. So when we given this kind of signal, if we want to clip some portions, if we want to clip completely positive cycle or completely negative cycle, or some portion of the positive cycle and some portion of the negative cycle, so which we suppose we want only positive cycle, 10% of positive cycle we want to clip it, we can use this diode and some battery along with this network, and then we can clip. So this is a simple example for positive clipping in this case. So it will achieve only negative cycles. So this is the diagram for positive clippers. Okay. So this when we see this kind of applications, so suppose if you put some like a battery, we can put a battery. Okay. So based on this battery also, we can clip this one, not exactly completely full cycle, we can required output, we can required cycle. Some portion of the negative clip also we can clip out. So there are number of clippers, positive clipper, negative clipper, two-sided clippers, positive clip with some polar battery with 1 volts, so that 1 volt can be suppressed of given cycles. This is the way to achieve this kind of clippers by using heart of the circuit or heart of the element is diode. So which allows and which does not allows in opposite direction. Next one is clamper circuits. This clamper circuit, so if you see this, this is the input signal where a sinusoidal signal having DC level is at origin. If you want to see this DC level shifted to some value, so then we can go to the passing through the clamper circuit. So the clamper circuit is in this case, first it's initially passing through the capacitor and then passing through the diode. So we will achieve this kind of DC level. So whatever the DC level at input side, now clamp to this level of DC signal. So this is the clamper circuits. There are also different kinds of clampers. Okay, so these clampers will be useful for at pulse and digital circuits. And then coming to the logic gates. So these diode are used in logic gates. Basically, diode act as a switch. So when we use this kind of diodes in logic gates, so it is a simple like OR operation. Except 0 0, remaining all cases will get 1. So if you are connecting, this is this way. A V plus supply voltage is given to A and B through the switches, and with the two diodes or PN junction diodes of reverse bias connected with the load resistor RL. So what happens when we are giving to the input to the 1 and zeros? Suppose in this case 2 zeros. When 2 zeros are given to the input, when 2 zeros are given to the input, then these two switches are open circuit and 0 is given. So both diode A and diode B is open circuit. When both are open circuit, so whatever the voltage, so here it is available 0 volts. So then RL 0 volts available across the load, which is equal to Y is equal to 0. Suppose when we are giving 1 to the diode A and 0 is diode B, then the diode A is conducting, diode B is open circuit. When the diode B is open circuit and diode A is conducting, the current direction from main power supply to through diode and the load resistor. When current passing through this load resistor, then the voltage across the load resistor will be, which will be converted to logic 1. Then so logic 1 will be available across the load. So then corresponding one, each time one diode is, first diode is on, second diode is off, then all the power supply directly connection to the output terminal. So what is the potential of this diode of this point with respect to ground? Then some voltage available across the load. If both are short circuit, in either direction, this direction and this direction also connecting, then current flow in the load. When current flow in the load, then what will be the voltage? The positive voltage applied across the load, then voltage drop across the load, which will be equal to logic high. Similarly, many types of gates, logic gates, we can connect through the diodes. So basic gates, AND gate, OR gate, NOT gate, and we can achieve this logic operation, logic truth table for those respective gates. This kind of applications we can see from the diodes. Sometimes diodes may be used in different applications by adding doping. So normal PN junction diode, if we see normal PN junction diode, when we make this P-type material and N-type material by adding impurities to the pure semiconductor, we will achieve P and N. If you adding this kind of ratio 1:10 power 8, every 10 power 8 atoms of intrinsic semiconductor, when we add one atom to the impure semiconductor, either pentavalent or trivalent, so we will achieve this kind of normal PN junction diode. Suppose in order to improve this application, in order to upgrade this PN junction diode used in different applications, just we can change this doping. So when we change this doping makes diode becomes many applications. So for example, this 10 power 8, for example, if we take this 10 power 8 to the 10 power 6, when we use 10 power 6, then 1:10 power 6 for Ginor diode, and also Ginor diode for germanium, Ginor diode for silicon. So this kind of ratio can be used in Ginor diode. will be used as an voltage regulator. In order to regulate that fluctuations happen in the input signal can be regulated to a constant voltage. And when we move to further 1 is to 10 power 3, when we use this kind of doping, so as we increase doping, heavily doped on p side and n side, then this 1 is to 10 power 3, every 1000 atoms of intrinsic semiconductor, we can add one atom to the impurities. Then the diode becomes like an avalanche diode. So this avalanche diode can be used in high power, high speed applications. So Ginnar diode, avalanche diode, light emitting diode. When we use light emitting diode, then we can use in different applications like displays. Okay, in order to display the digital signals, so we can 7-segment display. So when we use all 7 segments connected in a shape 8, then among by using these 7 elements of the LEDs, we can generate any decimal numbers or binary numbers, so that this LEDs, whatever the LED, the principle of LED, which gives the like voltage signals, electrical signals, and it emits lights, and also photodiode, it takes the light at the input, and it will generate the current flow in the photodiode. So this photodiode can be, the LED photodiodes can be used in optical applications, fiber optic applications. So likewise, by changing the doping of diodes, it makes many applications. It becomes many applications. So numerous applications can get from this diode. So far we studied in the previous lectures operation of p-n junction diode, and when we came to know about this operation, then when we changing the characteristics by changing the doping levels. Now coming to the diode switching characteristics. So have you ever thought about the diode switches from on state to off state and off state to on state immediately? So when we think about it, it's not true. So what does it true? The true thing is that the diode never responded for the logic 0 to logic 1 or on switch to off switch from and also from off switch to on switch. Let us see that why diode does not respond from one state to other state or one forward bias to reverse bias or vice versa. If you see this diode switching characteristics, so there are 2 important parameters need to be required to note. p-n junction diode operated in forward bias and p-n junction diode is operated in reverse bias. What happened when p-n junction diode was operated in forward bias, immediately it will shifted to reverse bias. So in this simple graph which represents that when we apply the forward voltage and suddenly when we move to the reverse voltage, what happens? So there are 2 important parameters: forward recovery time and reverse recovery time. Whenever a p-n junction diode is operated in an open switch or operated in reverse bias, then immediately it will switch to forward bias. So then whatever the stationary, like all the equilibrium charge carriers responded immediately and moved from these charge carriers from one region to other region. The majority charge carriers move across the junction. Then the time taken to respond these charge carriers and move together towards to the junction will be very less compared with the reverse recovery time. That's why it does not matter that how the forward recovery time. So and also it's not at all problem with this forward recovery time. Only the problem with the reverse recovery time. Reverse recovery time. So we will focus on it. So when we take a PN junction diode operated with a reverse bias, then immediately when we switch it to forward bias, so it won't respond immediately. What is the reason? Is because of the reverse recovery time. What will be the reverse recovery time? When we see this figure, so whenever the PN junction diode is in forward bias, and immediately it moves to reverse bias. So we know that the simple operation of PN junction diode in forward bias. In forward bias, what happened? This majority charge carries from P side to N side. All the majority charge carriers of holes move from P side to N side. All the majority charge carriers of electrons move N side to P side. That means all the majority charge carriers from P side cross the junction and enter into the N side, and it will be treated as minority charge carriers in N side. Whenever all the charge carriers of majority charge carriers of electrons, due to forward bias connection, they have a tendency to move from N side to P side, cross the junction, enter into the P side. Then whatever the electrons when enter into the P side, then they are called to be minority carriers in P side. So now, due to this minority carriers in the P side and minority carriers of holes in the N side, current flow in the PN junction diode, that can be represented with this forward current. Now, when we switch up this one from forward bias to reverse bias connection. So, for example, this is the switch, forward bias. So, initially it is in forward bias. So, immediately I am opening this switch. Initially, this is forward bias. Immediately, I am opening this switch. When I am opening this switch, so this diode does not respond immediately to be as a reverse bias PN junction diode. So whenever this move from this forward voltage to a reverse voltage, immediately that current flow in the PN junction diode shows minus IR, because whenever this PN junction diode immediately connected to reverse bias, whatever the minority charge carriers of holes in N side, whatever these holes when enter into N side, they are called to be minority carriers in N side, and minority carriers of inside the P, which are called electrons. So these electrons of minority carriers in P side, minority carriers of holes in N side, they have trying to get back their original position, get back to their steady state position. So whenever immediately they are returned back to their position, the moving of return back, which gives the current flow, negative current direction, negative current flow in the PN junction diode. How much time it will takes? The time it takes from, for example, it is a T1 and it is T2. The time takes to recover, to return back their original position, so is called this storage time, minority carrier storage time. All the minority carriers in the opposite region return back to their original parent region, so it takes time from T1 to T2. This is represented by minority carrier storage time, and which is mathematically represented with the TS. So once it takes this much of time to return back, so the flowing of minority carriers from their opposite region to the original region, so this kind of time it will take. Once reaching to their original position, then they have trying to reduce their speed and reduce their gets to transient mode to steady state mode. So the time take to to settle down these minority carriers and enter into their parent region, and it will be treated as majority charge carriers have holes in p type and electrons in n side. These majority charge carriers now slowly settle down to gets zero, their equilibrium position. So this is called transition interval. The transition interval is the time taken for this majority charge carrier in p region of holes and the majority carriers of electrons in n region settle down in this period. So slowly they have the current flow decreases until T2 to T3 times. When it is reached to T2 to T3 times, then it will goes to steady state, and then diode becomes in reverse bias. And then diode becomes reverse bias. There will be no current flow in the p-n junction diode. So this much of fraction of action happen in p-n junction diode when it switch from forward bias to reverse bias connection. So we simply think that it is a forward bias current flow, reverse bias does not current flow. But in real practically, in practical, the diode switching having different timings, okay, which is called like forward bias timing. So whenever it is a diode in forward bias timing, and it is my storage time, and it is transient time. So here I am talking about reverse recovery time and like forward recovery time. So forward recovery time, it's sometimes, most of the times we can neglect, but a reverse recovery time we cannot neglect in practical applications. So that's why we can take into consideration of this reverse recovery time is equal to sum of the addition of this storage time plus this transient time. Here we can see that when the diode is in forward bias and immediately switch to reverse condition, the diode will still conduct current for certain amount of time. Okay, the time period for which the diode conducts electricity after switching the voltage from forward to reverse, still it is in a state of conducting position. The time taken for this conducting action, which is represented by reverse recovery time. So this is the time for reverse recovery time, is the addition of storage time and transition time. So this is most important when we operated with these diodes in logic gates. So when we are taking into consideration of this logic gates timing diagram, so all the times that transaction between on and off. So every time, so this logic 0 to logic 1 and logic 1 to logic 0, so there will be always face a problem with this reverse recovery time. So always we are trying to reduce that reverse recovery time by providing some techniques for this normal p-n junction diode operation. So that's why in most of the practical applications of the advanced transistor level switches, so we can use this Schottky diodes. Schottky diode is one of the best circuit for to reduce the recovery time. So most of the this transistor switches, ECL. So when we see that emitter coupled logic circuit diagram, we can use this Schottky diode between base terminal and emitter terminal. Whenever base and emitter terminal gets reverse biased, then immediately by direct bypass of this through Schottky diode, then we can reduce the reverse recovery time of this off state to on state to off state. The reason for reverse recovery time is all that we have studied now. So when we reverse the voltage, we expect the diode switch from conducting to non-conducting state immediately, but Due to minority carriers, the reverse current flow through the diode and stays at measurable level for storage time required for minority carrier to return back to their majority carrier state in the opposite material. So after this time period, transition interval required for current to get back to level associated with the non-conducting states. Due to this reason, this recovery time takes a large time to get back. How to reduce this recovery time? The reduction of recovery time by following techniques. The first one is reverse recovery time should be small for high-speed switching applications. This is what we expect. This is what we always estimate. Always we are trying to become with this reverse recovery time. So the reverse recovery time depends on junction temperature, depends on rate of fall of forward current, and also this how can we reduce this when it is depends on these parameters? How can we reduce this reverse recovery time? The reverse recovery time can be reduced by shortening the length of P region. When we shortening the length of P region, which we called as like a small P type, small P region, and a large N type. Or sometimes we can take the doping also, when we change the dopings and adjusting the dopings. So best one is shortening the length of P region. When shortening the length of P region, most of the P junction diode, most of the P type emits the more number of charge carriers of force reach to N region. Then immediately they wanted to shift it back to from minority charge carriers in N type region, get back to the P region. When the P region is very thin or sharp, like a shorten of this P region, then the time taken to return back these minority carriers from N region to P region is very less. So that we can reduce the reverse recovery time of this P junction diode. And also by adding gold impurities into the junction by diffusion, for example. So when we use this kind of metal, like material, connecting material, like gold impurities into the junction, then a material, this conducting material having only number of electrons. So here, whenever the different materials at the junction, like gold and with the semiconductor material, the transfer from this conducting plate to the normal semiconductor material, then recovery time is very less. So that when we use this kind of gold impurities into the junction, so this way we can conclude that diode is simply it's switching from on state to off state and off state to on state, vice versa, within a fraction of time, but it takes time. So that is called represented by diode switching characteristics. So we can see that this forward recovery time or forward state and reverse recovery time. So we can always focus on the P junction diode manufacturing with the reverse recovery time gets reduced, so that we can use many high-speed applications. That is most important thing. So whenever we are going to design high-speed switches, high-speed electronic circuits, so always we prefer either diode or advanced diodes, like we can use transistor, even transistor also. So emitter base junction is also simply a diode. So here also we face the reverse recovery time between base and emitter terminal. So whenever we changing their characteristics, changing their reverse recovery time, then only it is possible to achieve high speed circuits, like in a BJT digital IC applications, in BJT ECL, how fast it is, in a CMOS application, like MOSFET applications, how can we avoid this kind of recovery time in these MOSFETs and FET applications. So So in all bipolar junction operations, we must use some kind of like a short key diodes or some other techniques by reducing this kind of reverse recovery time. So that's why we can focus on this reverse recovery time so that we can reach to the switches with the high speed applications. That's all about the diode switching and its characteristics and its applications and its timing diode switching times. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.